I'm Rahul Aggarwal. I'm the founder and CEO at Augtera Networks, and I'll take you through the overview of what we are doing, what we have built in this presentation, and then John will give an overview demo. So the problem that we started out to solve is the current networking tools are really built around this basic principle that you collect a lot of data and then let humans mine that data when things break or when applications, customers, or users complain. The tools are very reactive. There's a lot of noise, and they're not really built for multi-cloud networks. So that's the problem we started out to solve. And we really are reinventing how network operations work. And we are doing this by applying machine learning, by taking the data from various parts of the infrastructure, and instead of the humans mining the data, it's the machine which mines the data. And we produce what we call AI insights, which can be consumed either by humans or by automation tools. And there are a few key building blocks that we have. We can uncover patterns and correlations at scale. We do this by using largely unsupervised machine learning. We can collect data literally from any source that you can imagine in the networking infrastructure. We have built a slew of specialized network AI algorithms developed over 3 years of R&D and using production data from many, many large-scale networks. And the result is very actionable, high-fidelity insights. We are seeing significant transformative business outcomes in production at scale at Fortune 500 companies, hyperscalers, e-commerce, retail, finance, large service providers, managed service providers, you name it. And the first thing is that networks are really plagued by a lot of noise. Network operations deals with a ton of noise which comes from existing tools, very poor quality signals. They are very reactive. And so we built a lot of tech to eliminate the noise, be proactive, and stop the incidents. The second thing is, as networks evolve to hybrid cloud, multi-cloud, SD-WAN, software-defined networking, it's harder and harder to do end-to-end assurance and really figure out, is an application misbehaving? Find that proactively. And if it is, why is that? What is the actual root cause of that? And we'll take you through many examples of that as we go. DevOps is a big thing, but it's pretty difficult to adopt DevOps in network automation and network monitoring and operations because the old class of tools are really not built with an API and a DevOps mindset. We are changing that. And then there are too many tools. Over the last 20, 30 years, as networking has grown, so have the number of tools, and they're all designed for different use cases, different data sources, and we changed that. So my next slide will really start to articulate how our platform is put together. So we take data from various parts of the infrastructure, switches, firewalls, routers, load balancers, servers, physical or virtual, as well as from public cloud, SD-WAN, software-defined networking data sources, data lakes. And we take this data using homegrown ingestion pipeline. We'll get into it more in our deep dive, which is highly scalable and very, very cost effective. So we have built SNMP ingestion. Some people will be surprised to hear that. Here we are a very modern company. Why are we doing SNMP? Well, it turns out, most of you know better than us, that literally every network out there has a large SNMP deployment. So to work with these networks, you sort of have to really deal with SNMP. But then to take these networks to the next generation architectures, we have very, very optimized implementations for gRPC, GNMI, OpenConfig. We have a ton of syslog technology. We'll talk a lot about that today. Very proprietary, cutting edge technology around finding anomalies from syslog. We also do a lot with flow data. So we have integrations with SFlow, IPFix, even VPC flow logs, something which we added last quarter. We have our own API, which can be used for feeding us a lot of proprietary data as well as topology data. And we can take data from Kafka. To complement all of this, we have our own agent. And this can be deployed, it's a Linux agent, it can be deployed on VMs, on servers, even on switches, actually, as long as a Linux agent can be deployed on a switch. And it really enables latency and loss measurement to provide end-to-end SLA, which is very complementary data. What is not listed on the slide is TWAMP, which is another example of loss latency data. We have off-the-shelf integration with TWAMP as well. All this comes into our network AI engine. And this engine comprises 9 and growing number of proprietary algorithms, which are really a result of very specialized R&D over many years. This is across anomaly detection, both metric-based anomaly detection over hundreds of metrics, as well as log-based anomaly detection. Then we have the ability to automatically learn the model of the network. So we auto-discover the constructs in the network, whether it is in data center, in WAN, in SD-WAN, not just the routing protocols, but if there is a line card on a switch or a router, and there are queues on that, we discover all these constructs. And we use these building blocks to then do autocorrelation, again, using a machine learning algorithm. We are seeing significant outcomes of our technology. Some very large operators have spoken about that recently in a couple of conferences. You can look up AINet from April, ONUG, just last week, and they're seeing significant results, in terms of reducing outages, significant reduction in detection times, and so on. And our workflows can be consumed by various teams, all the way from NetOps, NetSecOps, CloudOps, and automated workflows. This part is very important. So we plug in directly into ServiceNow. We plug into Slack, syslog. We can emit syslog-based alerts. So the output of our platform can really be consumed in a very proactive way.
Yeah, just a quick question on the S-Flow and the IP fix. There's a number of products out there that will relieve network gear from having to generate net flow. You can capture traffic or copies of traffic, and then that'll generate net flow and IP fix for you. And it'll augment that with some proprietary information and tags. I'm thinking of systems like Gigamon and Keysight. Are you able to ingest IP fix and net flow with those extra tags that some of those other vendors put on them?
Yeah, absolutely. We absolutely can. We have, for example, VeloCloud is an example. We have an integration in production. We'll actually might even, depending on time, give you a demo today, where we take IPFix data with extra metadata that their product is adding. So we are doing this across the board because our pipeline has the ability to actually extract, custom templates.
Okay, perfect. Thank you.
I had a question back on the previous slide. You mentioned some specific vendors. What I don't see there is Arista. Yet it looks like all of the telemetry could be pulled from any switch.
This is I have to blame this on our marketing, because Arista is really one of our, not the only one, biggest deployments. We have only space for only so many logos, but I'm glad you asked that question. We are in production across all major vendors you can think of: Juniper, Cisco, Arista, F5, Palo Alto, Brocade. We actually have very large deployments with even Dell Sonic. And you're absolutely right. One of the powers of our approach is that we can integrate with literally any vendor which adheres to these standard-based protocols. Now, of course, it turns out that things like syslog, over the years, vendors have done a lot of proprietary implementations, and we have done a lot of work with syslog to actually extract those proprietary syslogs as well, which don't conform to RFCs. But generally speaking, using these standard-based protocols gives you massive leverage to work across a very large customer base, and Arista obviously is a big one.
A couple other questions I have for you. So are most of your customers enterprise, SMB? What would you say your average customer profile is?
It's really enterprises, service providers, managed service providers, anywhere from medium to large network infrastructure footprints. That's our majority customer base. But we are beginning to get more and more adoption and interest from customers who have smaller network footprints as well.
Okay. And then one other question is, do you work through partners or sell direct?
It's a mix. Yeah.
Okay. And are you on anyone's global price list? Any of these?
Yeah, we actually are on Dell's price list.
Okay.
You can buy us through Dell. So this slide just explains the basic principle of how our anomaly detection works using metric data. So we do, as I mentioned, anomaly detection on metric data and log data, text data. This is for metric data. This is a production example just to illustrate how it works. So we learn patterns automatically from the data. And this is what people would call unsupervised machine learning. In this case, this is a pattern on an interface on a router. So we can construct models, our algorithms can construct models on any granularity. It could be an interface, a CPU, a line card, a device, or all the traffic coming out of a data center, for example. So just sort of keep that principle in mind. There's a lot of flexibility. This example is on a specific interface on a switch, and that first red dot shows an anomaly when the traffic started to degrade, and augtera started to generate anomalies. 3 days later, the hardware actually crashed. This was a production example before the customer had confidence in our software and we were in a trial phase. So 3 days before something really went wrong, the machine started to say, look, I'm seeing a significant change in pattern that you need to pay attention to. And that's the principle of our metric-based anomalies. We do this across hundreds of metrics: TCP loss, retransmits, CRC errors, packet drops, queue lengths, CPU, memory, you name it. But this is the principle, and got multiple different algorithms for doing that depending on the metric type. And we'll get into that more in the deep dive. The other thing we have is our zero-day syslog anomaly. And I will not spend much time on this because we have a whole syslog section. But essentially what this technology does, which hasn't been done before in the industry, is that we can find unique syslogs automatically. So without you knowing what you're looking for, the machine can tell you when it finds something unique that's relevant, you haven't seen it before. And it uses a combination of natural language processing and machine learning techniques. The other thing which we do is autocorrelation. So I alluded to the fact that we learn the model of the network automatically. Since we can learn the model of the network automatically, we use that, and we use all the events and anomalies to automatically correlate what's relevant and what's related. This is a production example. Here, there is a switch at the bottom which had an issue, but it did not really emit any alerts. That was the nature of the issue. All the neighbors, they gave link and BGP alerts, but the operator, instead of getting 8 or 9 tickets or alerts, got 1, because the software was topology aware and it applies machine learning techniques to put these events together, and hence it can learn from different layers. It's multi-layer available, and it also has the ability to learn from different protocols, different data sources, and you will see that in a minute in a demo.
How long does it typically take to train the system, or is there some well-known metrics that are already fed into it? But everybody's network is kind of, people like building snowflake networks. How long does it take to learn my particular network on average?
Yeah, it's a fantastic question. So as I mentioned, we have multiple algorithms, and depending on the type of algorithm and the type of metric, the minimal learning period varies. A lot of algorithms require about 10 days of data to start producing reasonable results. Others require more like 30 days of data. But anywhere from 10 days beyond, you can start getting results, and they improve over time, of course.
So on the previous slide, you had ended that you're detecting operationally relevant logs when they first occur. And I think it kind of goes back to that question, is how are you deriving that something is operationally significant?
Yeah, so I think in terms of logs, I would defer that question till we get to the syslog section. I think it's a much longer answer.
Okay.
But in terms of for example, if you apply a question to say metric data, right? To figure out something is operationally relevant, it's we can abstract your question to a much broader question.
Yeah.
That the machine finds something using one of the algorithms we've got, and the machine says, here, there's an anomaly. So mathematically, you can use the best algorithms you want. It's an anomaly. But the operator might say, I don't care. So because operationally, it's not relevant. A good example would be, say, packet drops on top of rack switches. What often happens is that top of rack switches, you will find packet drops in large data centers. They happen all the time. And then sometimes they spike. Most operators we're working with don't care as much. So then what you need the machine to do is to take all the operationally relevant metadata and give the operator control, because operator says, you know what, I don't care about packet drops on top of racks, but I really care on the super spines. And you can really control both the input and the output of our algorithms. The simplest way would be to say, turn on packet drop anomalies, but we have the concept of ad hoc views, where you can just mine or notify packet drop anomalies on, for example, super spines. Or you can say, you know what, I really care about traffic anomalies on my interconnect from my data center to AWS. I don't really care about it so much in my fabric. That's how we think about what's operationally relevant. The other thing we do is we also let operators give us feedback. So you can give feedback and say, you know what, you give me this anomaly, it's not relevant, it is relevant, so on and so forth.
So I'm going to repeat just a portion of that back to you just to make sure I ingested that properly. So if I have generally speaking, my networking environment, I care about route flaps. I care about BGP bouncing up and down. But in an area where engineers are testing, I can say, well, I don't care about those BGP flaps over here, but on my internet-facing links, I care about those BGP flaps.
Perfect example, absolutely.
Okay.
Yeah.
And to kind of even build on that, so you said there's kind of that feedback loop. If there's a kind of an event is triggered, hey, we noticed this, and the operator can kind of look at it and go, yeah, this wasn't significant. You mark it that way. The AI then kind of learns this isn't a big deal. We don't necessarily need to alert, or we can increase the threshold.
That's right. Yeah.
Cool.
Yeah. Yeah. I think it's the former. We don't need to alert. Yeah. It's not the tech doesn't really use thresholds, but yeah. So I'll just do this very fast. I want you to remember that we really are working across the infrastructure: data center, branch, campus, SD-WAN, multi-cloud, and most of this is shipping. Some of our cloud capabilities are developing. We'll talk more about that in the roadmap. And we are doing this across various layers of the stack. The multi-cloud traffic represents the underlay or the network infrastructure layer. TCP represents really, just the layer above. And then, of course, what do applications care about? End-to-end performance. And what is not on this slide is you can also feed us proprietary application data. Simple to evaluate. It's, all of you know this really well, that this is the APIs we are using are passive, right? So it is not intrusive. We've done a pretty good job of.
Finish this and let's go back to the other side.
And we made it easy for you to evaluate. It's reasonably plug and play. We call it autonomous machine learning, where you don't have to really, mess around with configuration and tuning and controlling and so on. But Jeremy, please.
So please go back to your previous slide. You had mentioned something about custom application telemetry. Can you talk just a little bit about what that means?
Yeah. So I'll mention a little bit and then we'll come back to it again. So see, in the beginning, I said that we can take data from Kafka. I also said that we have our own API. So let's say that I'll give you a really good example. Let's say that the application team has retransmit data that they really care about, or application, or let's say you're a financial trading house and you have ticks which are being lost. Let's say you've got that data. You can feed that data to us, which is sitting around either on your server or your app, either using Kafka in JSON, and you can dynamically map that. So because you'll have proprietary data, we don't understand the format, but we have an API where you can go to feed that to us using JSON, go to our configuration and map your field. Your field might say Jeremy ticks, and map that to an augtera value, dynamically. Or you can say take the retransmits and map that. So that's one approach. Second approach is we also have an API which uses protobufs. You can feed that to us. So a couple of ways of doing that.
Okay. Have you seen anybody ask you about using like ingesting open telemetry from like that kind? That's kind of where I was going with that.
Yeah, open telemetry has come up a lot. It's on our roadmap, but we are not shipping it today, but it's on our roadmap.
Okay, cool.
Actually, this is a good spot to ask. My question here is with the work from home times that a lot of people are in, what I don't see on here is, agents or metrics to help, with that type of stuff. Do you have a solution for that? We're seeing some of that from other vendors in kind of this space this week. So that kind of piqued my interest to ask if you have any solutions for the work from home.
A work from home. Okay, I was going to ask you. So we have an agent, right? And the agent can be deployed. It's a Linux agent, very lightweight, and it's used for latency and loss measurements, end-to-end latency and loss measurements, synthetic probes. So we do have an agent, and we do machine learning on that.
Kind of a quick demo, be a bit of a video kind of to set it up a little bit, and then I'll show you some live views of our software. The best way to kind of illustrate augtera's power sometimes is to kind of use hypothetical situations. And that's what we've done. We have a lab we use. We can kind of demo this ad hoc for people, or they'll give us scenarios and we'll build these scenarios in our lab. And so one of the things we mentioned earlier is that we do autocorrelation using topology. So in this case, it's a data center, and we have a leaf spine set up with servers in it. And there's a maintenance happening where they're doing a configuration change on a BGP prefix list. So they're modifying, obviously, the BGP control plane layer. Now, it's happened sometimes when you're doing maintenances, things happen that you didn't expect, and that's what happens in a scenario. Now, during this maintenance, we start to see, I think I'll use the annotate button, is this link right here starts to flap. And it goes down, it comes up. When that happens, things in the network, we get signals from the network, like, link down, link up. We start to get BGP, adjacency changes, things like that, LODP. Once the link comes back up, though, then we have more things that kind of were unexpected. So in this case, we now get like traffic drops in the network. Oops. And so that causes a problem too. So we have new traffic drops that weren't there before. And finally, what happens is we actually see this box down here is running a firewall. This isn't working very well. We'll stop in a second. But basically, this box is running a firewall down here. And it starts to, every time it blocks a connection, it sends a syslog message to augtera. So we have a pattern of normal blocked firewall messages. Now, what happens is after this maintenance, it blocks a bunch of new connections. Augtera sees this spike or rate change as an anomaly as well. And so what happens then is we take all these signals, things like syslog, et cetera, and we put them into one correlated incident. So we're going to use a combination of features of augtera. Anomaly detection. We're going to detect anomalies for discarded traffic and for the spike in syslog rate. We're going to pull in traps from the devices. We're learning metrics. We're pulling metrics to the interfaces which feed our anomaly detection. And we're going to correlate this to a single incident. Now, the other power of augtera is we can have this smart ticketing or intelligent workflows where we can do deduplication. So if we get a bunch of things with the same thing, we can deduplicate that to a single thing. Or, if it's a real scenario, we probably would just actually suppress this because we know there's a maintenance going on, and we can talk to the lifecycle software and say, hey, if there's a maintenance going on, still produce the incident, just don't notify anybody because let's just wait until the maintenance is over.
When you said that word, we talked to the software maintenance, blah blah blah. For I know this is a maintenance event. Explain how that happens. Do we just send a post to your system saying maintenance is happening, or ball game is happening, or
Yeah, we actually have this in production at a couple of very big, large providers.
Yeah. So one of the key pieces of our ingestion is to actually take a lot of meta information from the customer networks, right? So we have a production use case where there are about 1 million interfaces, right? And now a customer actually goes on an interface, changes our description because they're putting that link in a maintenance mode. And they expect us to actually react to it and not create tickets because, otherwise any link flaps on that maintenance ticket will create false positives, a lot of alerts. So we are able to ingest this using, outbound API, push model, any such thing, whether a device is in admin state, up, down, is it operationally up or down, is it in test mode, is it in maintenance mode, all of those attributes, right? We're able to take it, and not only we are able to apply those attributes to our network model, but we are able to apply those attributes to every single piece of data, metric, events, which is flowing into our pipeline. So for example, if there's a syslog from a device which is in maintenance mode, and the syslog happened to be one of the patterns that the customer wants us to ticket, we will not ticket because it's maintenance mode, right? So this comprehensive knowledge of the network is there.
So, which is great. And I'm not going to look for the answer right here, but what I'm curious about, if you have documentation on it, is like, how granular can we get? For example, if we're doing a circuit maintenance, we're not doing a device maintenance. We just care about this interface. Or if we're doing, some changes to our BGP WAN, configuration, we know that we're going to cut over a BGP session from X to Y. So it's not even a interface maintenance, really just at a BGP maintenance level. So again, not looking for the answer here because it can get really complicated, but if there's documentation about how granular you can specify the scope or impact of a maintenance activity, I would be interested in seeing that.
Absolutely. I think we can go into details, but just to answer, it will be as granular as a network construct. So, what we define in Augtera as objects. So like, queue is an object, an optical lane, component, CPU, memory, right? These are like real physical things. Protocols, of course, exist in the MIBs, right? So we are ingesting all of these, and that's the granularity that you basically can work off, right? And then there is aggregation all the way.
What you'll see is I'm logging into multiple boxes. And the first box in the upper left is a TCP dump, so you can actually see things happening in real time. This is off the switch generating some of the SNMP traps and link down traps. This box 2 here is where we're actually taking interface up and down, like just manually kind of doing it to force the scenario. And when I do that, you see, okay, we got some traps coming in. In this case, I'm waiting for a link down trap to show up, which is a hold down timer, so it takes a few seconds for that to happen. Once that comes in, I bring the links back up, and then to this right box over here, I start basically a script that generates excess traffic for the interface. It's more than it can handle, and so of course the interface drops the traffic. And then the last part of my setup here is this box 4, which is basically me kicking off a syslog script that indicates a spike in firewall messages. So that's kind of the setup. It's a simple one to do, but it highlights, again, multiple signals and anomalies in a single incident. For the sake of time, I'm going to pop out of the video, because that was me just setting it up, not super exciting, and show you what it looks like. In the first case, just to know is you'll see that we can get these things, I'm going to scroll up, as incidents. So in this case, the operator got a snapshot of the topology affected. They can click the link and go straight to the incident in our software. So I'll have a couple more of these I'll do today to kind of show you the full workflow, but that's one way to consume this type of event. Now, once they're in our software, they go to the event, and you can see some context, time, how many events were correlated. But I think one of the most cool things the demo is people like pictures, is to show the actual event happening. So as I zoom into the network, my mouse, and you look over here to the left, you see like 4, 5, 6 of 22. It's actually showing you the events play out on the devices. Now, this isn't the full topology. This is 1/6, 1/7 of it. But these boxes in red are the ones impacted. And because they're connected, and we know that because we know the topology, they are part of this event. Now, what you saw here just pop in, and I'll pause this, is interface out discard. So now we're saying is, links are down, links are coming back up. At the same time, I'll click the red dot, is we have this discard for this interface. And that's the augtera anomaly, and I can look at trends, and I'll show you in a second how you can do more. And we'll let this thing play through. You can click on any of these events, like, if I click on, BGP, for example, here, and you'll see that there's multiple BGP events, all from the same switch as it's changed states back and forth, all kind of correlated. I'm going to show you 2 more things, and I'm gonna wrap this up just because I know we're out of time. This is one way to consume the data. Look at this as an event. The second way to think about it is, all right, these are all the events in kind of like, a table. You can sort, filter, you can look by timestamp, you can look by device name, you can see different contexts about it, like, if the interface was admin up or admin down when it went down. Up top, you see devices and roles, and you can kind of click through this. So this truly is, so 22-to-1 ratio reduction of, events to incidents. And, and you could even, again, take one of those anomalies like the discards, click a few buttons and actually go to the analytics of that one. Look at discards for the last month, the last day at a 1-second granularity. It's you can get very, into the weeds if you want to kind of do more analytics about what this interface looks like afterwards or before this event happened. So that's kind of a simple example of autocorrelation. We have a production example. I can do it real quick. That's a lab, right? And labs are labs. You're like, all right, well, John, that's great, but show me what this might look like in a real environment. This is what topology looks like in a backbone network. And so this is an operator that we have running our software. They've kind of built this to how they want it. So it's not, it's not us doing it. You can see what they've done is actually they've built dashboards. In this case, we're showing a topology dashboard, and you can kind of see it right here if you can zoom in. It says last day optical anomalies on core links. That's a view they like. And what happens is, and the one below it says last day link down events. So they've taken events, overlaid them to topology so they can quickly kind of see as part of their daily operations if something's going on in the network. And so what you'll see here is you can click on the boxes, get context, but we have a bunch of, in this case, they are receive power alarms. So basically, you'll see that the receive power on a laser fluctuated. It's a very different type of pattern you might see on interface metrics where it's constantly going up and down depending on the interface traffic. These things are very, very stable. When you pull up the anomaly, in this case, you can get the context for it, you can get the graphs for it. And I'll show you kind of an example of that here in a second, where they go from this view of an anomaly to the actual trends of the incident. And trends is our way of thinking about like the real-time analytics of this interface.
Yeah, I just want to jump in and say one thing here, that I mentioned when I spoke, right, that we got multiple algorithms. So one of the more powerful algorithms we have is an environmental algorithm. And the environmental algorithm deals with, actually, we've got a couple of different ones. One is for optics. That's what we are seeing here in production. And we also have one for fan, for temperature, speed, and so on. Now, these things, the metrics on these sort of environmentals behave very differently from traffic, from discards, and so on. And you can see that here a minute back, what John had shown. You don't have to go back. Okay. But I think it's just keep in mind that these are very stable metrics. And if you were to apply thresholds on them or standard deviations on them, or for that matter, even more complex algorithms, you will get inundated with false positives. It's actually almost like a non-starter. So this is an area we did a lot of R&D on. We tried many things. We failed multiple times. But what we have now is actually producing really good results.
Yeah, a similar example. So this shows an incident for light levels. So same kind of thing where you have these 42 different alarms that are come in, and all for a single device, multiple interfaces. And that's what this operator is doing, is click around looking at the different readings. Now, again, what I'll show you is as he clicks on one of these anomalies, you can see more context about the anomaly. And I'll pause it here. Looking at a short view, if you go look at a 7-day time series, you can see, like Rahul was saying, this pattern is super consistent. The slightest adjustment right here is the anomaly because of how tight this pattern is. And it's optical. Optical really shouldn't change unless somebody does something in the network or a laser starts to deteriorate. And so in this case, they go, yep, this is interesting. I want to go look at this in more detail. They go from the anomaly view to what we call an analytics view. And they can see, and I'll fast forward here, where now you're looking at the same data in a kind of a time series view. They can see when this event starts. They can zoom into the event. And now I think in a second, they're going to switch it to like a 1 minute granularity to see exactly when does data change. And this is all happening kind of real time. You can kind of see that pattern change right here in the middle. So this again drives an event or a notification to the operator, then goes into investigation to understand why this optical degradation happened. Those are two scenarios of topology in autocorrelation to kind of reduce noise and find anomalies in the data.
So with that, how you had the two graphs there, one was, I think it was power and the other was temperature. Were those two graphs kind of specific? Like these two were anomalies and it was specifically showing those because they both showed an increase? Or was it like that was the default view?
No, it's a good question. Yeah, so in that case, for optical, we look at 4 or 5 different metrics: power level, receive power level, transmit power level, bias current. So if multiple metrics are anomalous at the same time, they become stacked in that graph. Because last thing we do is, all right, okay, this happened, what else happened? And you got to go figure it out on your own.
So when you're engaging with your large service provider customers, I'm sure they probably had, Prometheus or some massive thing that they already had in place that was collecting syslog and metrics and flow monitoring, everything. Do they have to duplicate that data into your system, or do you syndicate with their systems in a way so that it's not like, duplicating the data like a million times to a million different systems?
Yeah, I'll take that. Just one quick thing on the previous question. Our anomaly detection algorithms are also multivariate. So they can deal with multiple metrics at the same time. Something to just keep in mind. Jeremy, your question. We have actually 2 or 3 different variants happening. In some cases, our customers connect their data lake, for example, Prometheus, with our software. So their data goes to Prometheus, or for that matter, could be Elasticsearch, and then comes to Augtera, right? And there is no duplication. Augtera keeps only the data which is necessary for machine learning. The second scenario is we've had cases where customers are, whatever data lake they're using cannot actually handle all these different types of data sources. So then they give some to Augtera, leave the rest there. We've also had cases where customers started out by using us for machine learning and then have, in the models I described, and then have actually migrated from their data store to us, because we can handle all these different data sources and keep it for historical lengths of time if they so choose. So we give operators a lot of choice in how they want to do this.
Okay, and just one follow-up question. There are some cloud-based monitoring observability systems out there that do offer, quote, fire hose type capabilities. Do you have already built integrations with those companies, on a data sheet, or that you can talk about, or that you could,
Yeah, so, for example, depends on what kind of products you're thinking. Like, for example, Splunk, we have an integration. Some others are on the roadmap, but yeah.
There's a massive amount of information that's been taken in here. What kind of horsepower is needed to chew through it, and are you going to be covering your deployment models? Is it cloud-based? Is there on-premises solutions?
So we have 2 deployment models. Either we can be deployed completely on-prem or completely as SaaS, or for that matter, hybrid. The software is deployed on a set of VMs. It could be bare metal as well. It's you can say it's a microservice-based architecture. We've got 30 plus services. Each one of them can scale horizontally. So that gives you a lot of flexibility. Just to illustrate, your question is super critical, because with machine learning, the cost economics of it, right? People don't talk about that. We did pretty much our entire stack is written from the ground up. Our algorithms are written from the ground up. And so to give you a sense, with one large network with about 12,000 or so switches, we are handling the entire infrastructure with machine learning on about 18 or so VMs, something thereabouts. And not all of them are high end. A lot of them are actually, a 16 core, 32 gig machines. A few are more higher end VMs. So we are very, very sensitive to being, cost economical.
I mean, there's lots of options for deployment. It was just, like you said, each one comes with a cost, and you have to evaluate how it's going to be operated. Operating on premises might incur more costs if you're paying your own operations. Is there different licensing for SaaS offering as opposed to on premises?
The licensing is the same. We encourage our customers to go SaaS.
Oh.
And that's because I think it's better velocity in terms of feature rollout. So we have given some incentives for SaaS. So pricing is a bit lower for SaaS. The other thing also is we have paid a lot of attention on how you do SaaS. So we deploy our proxy collectors on premise. They collect the data from your secure infrastructure, and then you send it over TLS to our SaaS. So a lot of thought has been given on how you do that, because that itself is an engineering problem. Yeah.
Yeah, that was going to be my next question. I've got some customers that have, highly secure OT networks. So it sounds like you have solutions for that as well,
Yeah.
to be able to extract that data.
Yeah, actually, and we've learned over time, right? Things which you don't anticipate. Like we've got customers who are sending us data from their internal infrastructure. And even though we are sitting on premise, our collector is sitting on premise, they want TLS from that infrastructure to our collector.
Mhm.
And we support that too.
This collector, is it viewing any of the payload, or is it just based on header information?
Oh no, it's not looking at the payload at all. So let me explain that a little bit more. If you have so what we call like an on-prem installer, which is just a proxy installer, right? And its whole purpose is to basically sit where your network is for security reasons, and gets data and pushes to the cloud. If it is SNMP, of course SNMP has to look at the SNMP headers and parses it, and of course decodes it and sends it to the cloud. So in that sense, SNMP protocol will do its protocol bits. But but let's say take syslog as an example, right? So syslog will be just sent as is opaquely. The on-prem is not looking at the data itself.
Are you keeping any of this information for forensics purposes, or is it just processed in real time?
It's processed in real time, and even the retention is dictated by the customer needs, right? It really is a customer decision, and different data types will have different retention, different needs. So if you have flow data, customers might say, well, do it for like a week versus traffic, which might be for a month, and so forth.
But just to add to that, if you want to keep it for forensics, you can. The retention is configurable. But of course, then that'll add storage and resources and all of that. But the key, obviously the key power of the tech, the differentiation is all the real time and the real time machine learning.